Hello, my name is Matthew Soriano.
I'm Jesse Hernandez.
John Stratton.
And Surya Tevritiller.
And we are here to answer the famous question, how many licks does it take to get to the center of a Tootsie Pop? Or, more specifically, the rate of change of the Tootsie Roll Pop's volume. We are going to determine cereal's mouth sucking power on the Tootsie Roll Pop. First, we will have to find the initial radius and calculate the initial volume. Using the formula 4/3 pi r cubed, which equals the initial volume, the time frame of data recorded is 330 seconds. From the data, we will determine radius versus time, rate of change of radius versus time, volume versus time, and rate of change of volume versus time.
So to find the radius, we must first assume that the Tootsie Roll Pop is a perfect sphere. We took measuring tape and measured the diameter of the Tootsie Roll Pop, not the outer rim, but rather the inner sphere. Since the radius is half of the diameter, we divided our diameters by 2 to calculate the radius. For each 30-second interval that we sucked on the Tootsie Roll Pop, we then measured its radius. We repeated this trial 11 times until we reached the center of the Tootsie Roll Pop. Here's our data collected for each trial. To find the rate of change, we must utilize the slope formula y2 minus y1 over x2 minus x1. This will determine the rate of change of each of the respective points. To find dr dt, we must input the first and last values from the data in our chart. This will give us the average rate of change.
As Jesse previously explained, we use the slope formula y2 minus y1 over x2 minus x1 to find the rate of change of the radius. Some of the things that we noticed about the rates of change is on our 3rd, 4th, and 5th trial is similar, and on the 9th trial it felt like we had no change. On 10 and 11 we had the exact same change, but this was as we were approaching the center of the Tootsie Pop.
Let me show you how we got the rate of change of our radius. First off, we use the slope formula, y2 minus y1 over x2 minus x1 in order to find the change in the radius. I'll just show one example for time 30 to 60 seconds. We get the second y value, which is 1.349375, minus the first y value, which is 1.42875, and then we divide it by the second x value, which is the second time, which is 60 seconds, minus the first x value, which is 30 seconds. And then when you subtract the top values, you get negative 0.079375. And then when you subtract the bottom two x values, you get 30 seconds. And then when you plug that into the calculator, you should be getting negative 0.00265. We had to repeat this step 11 times in order to get our data on the next slide.
As Jesse previously explained, we use the slope formula y2 minus y1 over x2 minus x1 to find the rate of change of the radius. Some of the things that we noticed about the rates of change is on our 3rd, 4th, and 5th trial is similar, and on the 9th trial it felt like we had no change. On 10 and 11 we had the exact same change, but this was as we were approaching the center of the Tootsie Pop. Since we assumed a perfect sphere, we use the formula for the volume of a sphere as 4/3 pi r cubed. We then plugged in the radius of each corresponding trial to obtain the values of volume as it decreased. This chart shows the change in volume over the period of 330 seconds.
We derive the equation of the volume of a sphere, 4 pi r cubed over 3 is equal to v. We use implicit differentiation to find our dv over dt, or rate of change of volume. We input our average rate of change of the radius that we found earlier for dr over dt. This will help us determine dv over dt. On this chart, you can see that as we keep approaching the last trials to the end of the chart, 1 through 11, we can see that the negative scales down. So as you can see, the 0.06 doesn't change as much as trial number 11, which would be 0.0169, because there's almost nothing left of the lollipop and approaching to the center of the Tootsie Roll Pop.
Okay, so as stated in the previous slide about the formula used to find the rate of change in volume, I'll show a brief example for time 30 seconds on how we calculated this. So first we took the derivative of the formula for volume of a sphere, which is 4/3 pi r cubed. And that comes out to 4 pi r squared dr dt, which equals dv dt. Then to find implicit differentiation, we plugged in our values. So you get 4 pi times 1.42875 squared, and that's the radius at 30 seconds. Then we multiply that by the dr dt at 30 seconds that we showed in the previous slide, which is negative 0.00264164. And when you plug that into the calculator, you get negative 0.0677634 centimeters cubed per second, which is dv dt at 30 seconds.
The 1 and 2 and up. In the end, the power second speed is negative 0.04131 centimeters cubed per second. How we found this was by adding all the rate of change of the volume together, then dividing by 11, which is the number of trials that we had, to find the average rate of change of the volumes. The result is our number, and it has to be negative because it reflects a decrease of volume throughout the entire